Hello, folks. Can you hear me?
Yes.
Yes, hello.
Awesome. Awesome. Well, I have to jump off right at 7:30, so sorry about that. But let me just quickly give an update on what's going on with the row combinators paper. Let's see.
I like your text about types and categorization.
Oh, cool. Thank you. I
Yeah.
appreciate that. Yeah.
Yeah.
What did you like about it?
So this relationship between bisimulation, or just when you said relation between simulation and bisimulation. I know it's obvious, but when I was reading, it was like, oh yeah.
Yeah, I understand. Yeah. I mean, I think there's just a lot of the paper is just full of basically things like that, where there are a lot of things that are obvious consequences of some basic stuff, but people don't put them together. So for example, the most central theme of the paper, which is that since types classify all programs and some programs are simulations, types classify simulations. And if they classify simulations, then that means they can in principle be used to classify things in the world. Right? That's the basic idea of the paper. But this is, to the best of my knowledge, I'm the only one that has said this.
Interesting. Yeah.
Yeah, right. So it's an obvious consequence of the computer science, but nobody seems to be taking that next step, so to speak. And now of course there are two ways that classification scheme can go wrong. So one is that the types too coarsely classify programs, right? So we know this from functional types, right? So sort and shuffle do the opposite of each other, right? So sort will order the list and shuffle will unorder the list, disorganize the list. But their functional types are the same, list event to list event.
Yeah.
Right. So in that sense, the functional types are too coarse-grained to get good information about the intent of the program. So that would be one way in which the type program relationship could not support using types to classify things in the world via this path of simulation. And then the other one, of course, is it could be the simulations are too coarse, right? So there, I was just talking with someone about human behavior and pointing out that dolls are not very human-like, right? They don't breathe, they don't bleed, they don't reproduce, but there's some aspects of what it is to be human that they do capture, and somehow human children respond to those aspects. And so it can be that the simulations are too coarse, all right? And so there are two places where the relationship between types and the phenomenal world can break down. But if they don't break down in those two ways, then you can do that. And so then you can start asking questions about what does it mean for them not to break down. and again, bisimulation provides a really good answer, right? So if all equivalences that we can think of, at least computationally, come down to bisimulation plus filtering, then if your filtering is too coarse, then your biosimulation will, then your equivalence will be too coarse. And so, go ahead.
I'm thinking about a crash test, for example. You have a doll of the human, but for this purpose is enough, right? Because we are filtering all the other stuff. Reading is not important, so we can say, yeah, this
Exactly.
represents human.
That's exactly right. That's right. So for certain kinds of play, we can forget about the breathing. And so that's that's exactly right. So if you keep it more more faithful at both levels, then you're able to use types to classify things in the world. And by types, I mean, the types that we associate with programming languages.
I mean, if we can construct, if we can modify this type, we can be more precise in the ways that we want, right? So
yes, exactly.
This looks interesting.
Yeah, absolutely, absolutely. But the thing is that I think that people don't understand the import of this for artificial intelligence, right? I mean, they don't understand what this might mean in terms of our approach to classification of things. So that's why I felt the need to talk about it. The other thing is that we haven't even really explored the area from the point of view of just mathematics. So since again, it should be the case that all notions of quantity that have been put forward are representable computationally, right? Because that's kind of the point of a notion of quantity, is that you can compute with it in some way, shape, or form. So, I mean, if we take that as a given, right, there might be some argumentation on this point. Maybe we have notions of quantity that we don't want to compute with, or that our current understanding of computation doesn't quite fit. But at least initially we might say that they have to be representable computationally, or maybe they're not a notion of quantity. So if we take that point of view, then we can apply types to notions of quantity. But if we think about how numbers have arisen, it's been very haphazard. So it's the discovery of zero, post the integers, is a bit weird, right? The discovery of the irrationals. So it's essentially there's this kind of erratic, random walk through notions of quantity. But we confuse this erratic random walk with having with the innate structure of the notions of quantity, and that certainly isn't the case. But we could use notions of types to go after more systematic classification of notions of quantity. So, for example, Conway games have been used as a representation scheme for all of the notions of quantity that we have encountered so far. So you could start with. I mean, I should be careful. Conway games are not particularly good at, or don't give us any special insight, at least as far as we know right now, on the complex numbers, the quaternions or the octonions. So there might be something there. Okay, so it looks like we'll have to move rooms for the Casper Stand-Up next week. We'll move over to 322-705 6432. I think that's right. Let me just check. Yeah, I think that's right. I'll post it later. So beginning next week, we'll switch rooms.
So maybe in the first grade, we should not teach kids numbers, but types.
Something like that. I don't know. It's a tricky question. It's a very tricky question. But anyway, yeah. Well, read. I encourage people to read the article and see if they have any feedback. One of the things that again is bears discussion is that because bisimulation is parametric in the notion of action, it's not limited to Turing complete. So I don't think that a lot of people understand that there's this hierarchy of computation that extends infinitely beyond Turing complete.
I think it's deterministic, quantum, equal and opposite logical action. The only thing that exists, what exists is the Hermitian, complex Hermitian conjugate, where we have top down and meeting the bottom up.
It goes way past that. There's an infinite tower way beyond that.
It's by simulation to the absolute limit where they're equal and opposite.
Okay, sure. I'm just talking about the tower of computation that's related to notions of oracles, right? So there are machines that can solve the halting problem for Turing complete machines. Now, they can't necessarily solve the halting problem for themselves, for the machines in that class, but they can for the lower class. And then there are machines that can solve the halting problem for that class of machines, and so on and so forth. So it goes on infinitely, and because of this infinite tower, we might ask what if any notions of equivalence are available. And because bisimulation is is parametric in the notion of action, it can be applied to the whole of this infinite tower. So, I mean, the interesting point is that we don't know if we know we can give a mathematical account of this tower of infinite computational expressiveness. And in some ways it corresponds to the tower of transfinite ordinals, right? So there are ordinals that get really, really, really big, and ordinals that are even bigger than that, and ordinals that are even bigger than that, and so on and so forth. And there's a correspondence that can be drawn between those ordinalities and this tower of computation. But bisimulation can be applied at every level because you can adjust what can be seen by the notion, by the notion of action, right? So biosimulation depends upon providing a notion of action, and that's and that's why it has power that I don't think a lot of the mathematical community has sort of taken to heart. It can be applied as a classification means across the entire hierarchy because of its parametrization in the notion of observation. Yeah, see, the thing with respect to quantum computing is it has a fixed notion of what constitutes an observation. So you have to, that's why it tops out. Now there might be ways to extend that or generalize that nicely, but
I think the idea of quantum causality is perhaps controversial, but it is what it is.
Sure.
It's discoverable, and that's this iterative process you're talking about of discovering it, where the possibilities are infinite. It's representation is finite, if it exists.
But moving on, got 12 minutes left before I have to jump off. I'll just mention that, let's see what we've got here. I've got, I don't have it screen share. So let me screen share.
Is it our resource something like, from higher level of computation, we are introducing research to solving the halting problem on this another level of computation?
Yeah, basically you're allowing yourself to run infinite computations. So things at the next level can take infinite time or infinite space to do stuff.
Okay.
Yeah, and in point of fact, the interesting thing is that we don't know where things in the phenomenal world live in that hierarchy. Right? And it really depends on one's ability to, if your ability to observe can change, then you can change your location in that hierarchy.
Like
so yeah, so you can have a science that lives entirely in Turing complete, that's very different from the science that lives at the next level up or the next level up. I mean, see, what I was trying to indicate is that biosimulation really sits at the heart of what we think of as science, right? What you're trying to do when you come up with a theory is to come up with something that biosimulates the world or the phenomenal world, right? And but you can't do that because the phenomenal world is too big. And so, in other words, you can't construct a proof because the phenomenal world is too big. So, but what you can do is you can falsify the theories. So and that's kind of the best you can do with science. So you can, but the point then is that you can have different kinds of science at different levels of computation and observation. So which we don't, and we don't know where we live in, and it might be that there are some beings that live at a much higher level and other beings that live at a different level, right? But they can still talk to each other. So it's a really interesting world. Very, very strange. But
right, but I think truth includes both.
Yeah.
Also includes the Bayesian knowledge.
Don't get me started on Bayesian stuff.
Science, I mean, that's, yeah. No, I mean, science has to include that, to be complete. But yeah, we want.
Maybe I'm not.
We know that it's ultimately deterministic, and that's what we're discovering when we bisimulate.
No, bisimulation works just perfectly well for non-deterministic computation. That's kind of its raison d'etre, right? The pi calculus and rho calculus and ambient calculus, they're all non-deterministic, but bisimulation supports those notions quite well. In fact,
right, but the operations are not probabilistic; they're discrete operations.
No, you can have probabilistic pi calculi. That's just fine. It's how
I
you.
guess what I'm saying is they're not necessarily.
Yeah, how you interpret the meaning of a race condition in the pi calculus or the rho calculus is there's a lot of freedom. You can interpret it as literally a race, right? So or you can interpret it as non-determinism in the quantum sense. So those are that part is left unspecified in the theory. But moving on quickly here. So I'm still slowly but surely filling in the rest of the implementation of the rho calculus, rho combinators paper. So I have done both the par, input guarded par, and I'm currently working on the input guarded replication. The code isn't here, but it's because in the paper I wanted to fix something because the reviewers were unconvinced that they could, they didn't understand how to take what was already there and do this case. So I went ahead and filled in the case precisely. So before I just simply didn't have this case because we had this equation here. So, essentially the way, let me see, this probably isn't big enough to read. Let me make it bigger. So essentially the way this works, and it goes up to here, right? So this was in the paper originally, and I cleaned this one up. I inlined a particular definition so that you don't have to go back and forth between two different equations. You can just see it all at once. So kind of, it helps to understand that there's this sort of super combinator, which is made of three combinators, right? So you duplicate, you forward, and you drop. And if we see what happens when you, if you run that combinator in parallel with a message that is running that combinator with a particular process P as its payload, then you see that you get a copy of P dropped out, right? And so this is exactly Milner's notion of replication, right? So you can, so if you, I think we did this last time, but I'll do it. It bears repeating. So we have, so on X, we're going to send this particular payload. That's what the message combinator does. And that's running in parallel with this thing, which is really just shorthand for these things. Okay, so since par is commutative, I can put this on the left-hand side and that on the right-hand side. So that's what's done here. And then when we put this on the left-hand side, we can just expand it to its definition. And so when you run a duplicator, that so notice that this duplicator can't interact with the forward and it can't interact with the drop. So we can rewrite this again, moving this to the right next to the duplicator. And so that will, so since the message is on the same channel as the duplicator's target, we'll duplicate the payload, which is this thing, at V and W. So we'll get a message of the payload sitting at V and a message of the payload sitting at W. And then we have the remainder of the stuff, right? Which is just the forward together with this, together with the original gadget. So then when we reduce again, this this gives you sorry, I'm just this interacts with the forward, right? So we have a message V interacting with the forward. So you take the forward and you flip it over past the W. So that places something sitting at X, the payload sitting at X, the payload sitting at W, and the drop. Since the payload sitting at W is on the drop, we're going to go ahead and start running whatever that payload is. So that's D together with P, and there's the message. Now we look at the just everything to the left of the par P, and that's just the top line there. So that's just the definition of replication together with P. So that's how that works. So hopefully that makes sense. Okay, so now moving on. So since we know that works, if we take the translation of P, but we guard it by getting the fresh allocator and the fresh name thing, right? So whatever we send on these two channels, that's what we're going to send into the interpretation of P. And we run that with the duplicator together with, and here we're not going to further update this thing, right? So it's kind of stuck at whatever the new thing came in as. So we always sort of fork off into a copy of the namespace that's sort of frozen at that point. And then we run that in parallel with the duplicator sending in left on in and P left on P. Then what will happen is when we run the duplication, this interpretation of P will be unlocked with in left for in and P left for P, right? So that's what will be sitting here. And then these two will unlock that for all subsequent drops of P. So it'll keep copying versions that have these names located. And then you just have to say what the X, V, and W are. And in this particular case, we just have to make sure that they're fresh from the names in P basically fresh from the names in P. So all we have to do is mention that and then build something that mentions that. So that's what these things do. So they're all fresh from each other and fresh from stuff in P.
Can I ask about, we have two messages at the end, and the channel, and the channel and the payload is the same.
Right. So
and-
basically, what's going to happen is every time we get a new copy, or get a new copy of this thing. So we won't get P unless we have an N and a P. But the first time the N and the P we have is, if you look, the first time we're going to send N left on N and P left on P. Does that make sense?
Yeah. Yeah.
So then,
yeah.
so then these things will be N left. So when we unlock it, oh, actually no, it should just be N left and P left. So N and P. Yeah, that's a typo. Sorry.
And the payload is left, right?
Yeah, hang on a second.
Okay.
So this is, yeah, that's a typo. Here we go. It's above here. Here we go. There it is. Yeah, it should just be N and P.
Okay.
Yeah, and then that will unlock that. I think I have the same typo down there. So down here, I think I do it on the right-hand side. Yeah, there it is. Yeah.
So we are just ensuring that in this new scope, we always send these two new names.
Yeah, exactly. Okay, so now let me. Yeah, there we go. So the main point is probably what I should have done is to put this over here, but we're the duplicator is just duplicating the whole thing, right? And so it'll duplicate this together with the gadget that unlocks this. So that's the idea. And so you need to do a little bit more in the input guarded version because you want to make a fresh name, right? So if you look at Yoshida's interpretation, which is down here, when she's interpreting input guarded replication, she makes a fresh name and then forwards from A to C and then replicates along C. And then does the where you you send on CX. So that's the idea. Yeah, I think, let me make sure I've got that. I've done the right interpretation. Yeah, that's it. That's the one. So just double check that here. Yeah, I got that right. Yeah, it's a faithful rendering of that. Yeah. Okay. So that means that when we're interpreting this, right, we're getting rid of the new. So I have to simultaneously run the interpretation of replication and the interpretation of new. So what we have to do, right? So up here, I have to here we are. So here is the notion of new. So basically, we listen on the P channel to get X, and then we send the fresh in, right? So X is being guarded in P, so whatever X is, it's got to be fresh. We know N is going to be fresh, so we use P to get the new N. We bind that to X, and then we update the N and the P so we don't have any collisions, right? And then so that's how new works, right? It's basically, as long as when you start, N is fresh with respect to everything, which you can guarantee by, using all the names in P and the construction of N. So N will be fresh at the beginning, and as we recurse, we always update N. So that's the idea. And so then we have to do that in this case. We have to combine the two interpretations. So you can see that that's essentially what I've done. Is I've mimicked the shape of the new, and then R is really where we're doing the duplication. And then there's the duplication, and then again I've sort of I've abstracted this away into a variable and then expanded it out here, and then we get the same stuff here. But I need to, oh yeah, I got that right. So that's good. So and so now I'm going to put the code in for that. Oh wow, it's 7:38. I'm way past time. But anyway, so hopefully that gives you a little bit of stuff to chew on, right? So the overall point is that whether we're talking way out at the top of how do I say this? The paper that I sent out yesterday was being able to speak at the strategic level at a much larger scope and scale. But when you're doing that, there are all kinds of ways that things can go wrong, right? Your reasoning can go wrong because you're at such a high level of abstraction, because you're looking at such a large scope. But the tools that we're utilizing, so compositionality by simulation, those tools make it possible to step by step go all the way down to the nitty gritty, all the way down to this level of reasoning without losing the thread. And that's the whole point. I mean, what is typically problematic in the enterprise development is that the architects are not working at the level of the bits, right? And so there's this gap between the developer experience and the architect experience. But my argument has been, with these kinds of tools, you can have this smooth, continuous transition between the architectural experience and the developer experience, right? And so developers can be architects can be developers, right? There's not a lot of this, it's really just, well, what are you taking as a component versus what are you taking as a system? And that's the difference. And so it's the same reasoning tools at every level of the system. So that's kind of the point, and that's how you get requirements traceability and reliability, and but also the ability to scale and build these systems out of larger and larger components. So far the object technologies have not given us that. That was their promise, but it didn't work out. But these tools do, because they give a crisp notion of what substitutability is, and they give a crisp notion of how to reason at a higher level via types, right? When two components share exactly all the same types, then they are, for all intents and purposes, the same component. There's no way to distinguish them. And so they are substitutable in all contexts.
Can we somehow relate this to our notion of packages or modules? because we have functional languages, but when we think about packages, everything breaks up, you know, right? When we are managing implementations, this is not very functional.
No, it isn't. It isn't functional. You're absolutely right. And Javier Leroy, the OCaml guy, attempted to solve that with his notion of object in OCaml, and then Martin Odersky attempted to take that idea over into the Java world with Scala. But it's still very much at odds, because we don't, how do I say this? Because what goes into such a scope is arbitrary, right? There's no sense of how these scopes are systematically built, right? And that's really the problem is, there's no good management for when you build a particular scope and when you break it up into two scopes or that sort of thing. That's all rule of thumb. It's all art.
Yeah, I was listening Odersky for modification on implicits, and in next version there will be like delegates and some other keywords, and I'm wondering at the end maybe we want the whole Scala language to define this kind of stuff, because we have special notion of how we manage implicits or these implementations, and it's not.
Yeah.
It looks like something different than the normal language.
Yeah. Well, it's a long, tough slog. Rolang is a first step towards something a little that has some other features, right? Essentially, the notion of monad needs to be at the core, right? Monad is the new object. But the problem is you can't rely on category theory as giving a good foundation either, because category theory is far too leaning in the direction of function. So that's a real problem, because functional composition is not good for concurrency. So category theory, it takes a lot of work to get category theory to support concurrency naturally. And by the time you've done that, you build a layer on top of category theory. You're no longer doing category theory. You're doing something else. And right now that the better something else looks like the mobile process calculi. So they're just better at talking about concurrency. And so the trick is how to wed what's good about category theory, which is the notion of monad, into the concurrent setting. And Rolang is essentially the reformulation of the row calculus with the for comprehension is an attempt to do that. But there's still more to go. I think that if we were to redo category theory with the notion of monad as the fundamental building block, we might have a better shot at this. But I think a lot of people would complain, well, but in order to express a monad, you have to have natural transformations and just a lot of machinery. And so how do you use that as the fundamental building block if you've already used so much of category theory just to express the idea? And the thought is that monads really correspond to comprehensions, and comprehensions are perfectly fine for set theory. So it's like mathematics has been founded on a notion of set theory for a long time, right? That's been an accepted foundation. And so there must be some way to sort of utilize the notion of comprehension as the foundation, but recognize that these are generalized comprehensions that correspond to monads. That's kind of the idea. And if you have that refactoring, then we might be able to have something that enjoys a lot of the good things about category theory without being so biased towards the functional point of view. But it's a long process to get to something that's has all the desiderata. But Rolang is an attempt to point out, the fore comprehension is really the centerpiece of any good language. It really needs to be right at the center. And I don't think people understand like how often this notion has been discovered, right? So the set theoretic computation is now hundreds of years old, more than 100 years old. The same idea was rediscovered in relational database theory, select from where, that's comprehension. It's the same idea in Haskell's do notation. It's the same idea in Scala's for comprehension. Python's notion of comprehensions. These are all variations of the same idea, and it is extremely powerful because go ahead.
Is this the case for generators also?
Yeah,
in some kind of different way, but
that's right. No, generators are exactly the same.
Nice. Okay.
Right. They're all cut of the same cloth. They all come from this idea of a comprehension, and the comprehension is at its heart monadic. That's sort of what makes it a comprehension. So, and the polymorphism that comes out of the monadic interpretation of comprehension is what makes it the right unit of reuse. But you have to place it in a concurrency setting. So that's why Rolang is structured the way it's structured. But it's still a far cry from where we need to be able to have a language that genuinely fully supports all the kinds of things that we want to do with packages. That's still further out. Yeah.
But packages in Rolang are just like continuations.
Well, I mean, you could say that objects in the module formulation of OCaml are just lambdas. There's more to it. Like when we think about the practical organization of software, there's more to the organization than just lambdas or just continuations. There's something else there that is not just art, and capturing that is tricky. All right. Well, I have.
It's all types. I have a brief update.
Okay.
I ran the gym test on TestNet with. Oops. Can I share screen?
Yeah, sure.
Oh.
There you
go. All right, guys. So I don't know if you can see this, but this is basically the get ticket problem, where each time you get a ticket, with the username gets a ticket, they get the next available ticket number. Okay, this can be problematical, but I ran it with Gary, and while we're doing the round robin, we had no issue with tickets of the same number being issued, which I'm not saying is necessarily a bad thing, but it's just seeing how the system behaves.
Mm-hmm.
Yeah, I don't think
I mean, the more concurrency you have, the more those kinds of things run into issues. Well, there's a round robin, you have very limited concurrency. You only have concurrency inside the row line code, not across deployments.
Yeah, and
As
you know,
soon as you have concurrent deployments, then you're going to run into problems.
Yeah, and it's so basic. I mean, we just have sends and receives. We just have channels. We don't, you know, it's utterly simple, but yet how we deal with it, and I guess it comes back to monoids. How do we express a ticket as a monoid?
No, it's the access to the monoid as a resource. The issue is the monoid. As long as you're using if multiple entities are using the monoid, they can get different expressions in the monoid at the same time, right? It's about the control of the use of the monoid as a resource. Think about it like a clock, right? So the clock is like a monoid. And if two people get to adjust the hands of the clock, right, then when someone else is observing the clock, they don't know which party to believe in terms of the adjustments to the hands of the clock.
Can we, in this situation, when we need some sequencing, can we see this in the future, that we have a separate shard or network which is just optimized for producing decentralized sequence, which is very fast, and consensus is optimized just for that?
Yeah, but then people who are outside of that shard, you know, you can begin, like, as soon as you take that point of view, then shards are sort of like light cones, right? And two different shards, you know, managing different copies of that resource. There's no causal relationship between the two resources. So it's like, you know, a space-like separation of light cones.
Okay.
Yeah, they're not causally related. So this is why, for example, I don't like wall clock time, because who's in charge of the clock?
I was thinking that the whole network is decentralized, because now if we want to have this sequence, one of these blocks will be orphaned, so we are losing something. What Jim is trying.
Yeah, but now you're assuming that everyone has access to that shard, right?
Oh, I was thinking that our existing mainnet have some connection to this another network, which is just for that. So we are like importing this data in our network.
Yeah, that's what I'm saying. So you have centralized control. That shard is the centralized control point for that resource. Even though all the machines that are supporting that shard are distributed all over the galaxy, that network is the central point for that resource. So if you had another network that claimed to be the central point for that resource, how do you adjudicate between them?
Oh, yeah. I was thinking that this is like the source for this kind of data, and
yeah, it's the source of truth for that kind of data, right? But this is what essentially you're assuming the solution to solve the problem.
Okay. Yeah.
Cool. Well, I completely blew my, I'll have to take that 30 minutes from another place. Okay, I'll see some folks. Yeah, so next week's Casper will be in 322-705-6432. So just so people.
Will we be able to record it next week?
Yeah.
Okay.
No problem. All right. Thanks, folks. I'll see some of you in Dev Stand Up in 3 minutes.
Great. Thanks, Greg.
Bye-bye.
Thanks. Bye-bye.
See you in a bit. Thanks.